So we'll have Bruce take it away again for the second session of the morning.
Great. So we ended last time with a little bit of a quandary where we had a nice homomessy, but we did not have cyclic sieving. So I want to show you a new statistic that will give us both. Well, actually, it's not new. It's a very old statistic that's going to give us both. So why is this not wanting to? Oh, maybe I just didn't. There we go. It'd help if I hit the button for writing. So definition. Suppose that we have a sequence I'll call the sequence pi with elements pi 1 through pi n. And this is a sequence of integers. I don't know why this pen is not writing well now. It really doesn't want to write integers.
Do you want to try to reset the desk whiteboard somehow?
Let's see, to reset.
Let me see how I reset mine.
Okay, talk me through it.
Well, it's telling me to set up mine, so I don't know how to unset up mine. Let me see if I set it up. You know how you draw the circle on your desk?
Oh, yes, let's go back to that. That might
Yeah,
work.
so I wonder
Yeah.
if you just click on the desk whiteboard button again, if it lets you know. See, once I do it, it's not letting me like redo it. That's funny.
Okay.
Um,
Desk whiteboard. Okay.
You can go through settings and then you have to do whiteboard and desk.
okay, thank you. So apparently you go to settings in front of you, Bruce,
Okay.
and
I
then
just created
whiteboard
a
and
new
desk.
whiteboard. Let's see if this is any better.
Reset desk whiteboard. There we go. So you go to
No,
settings in front of you.
this will work. Okay.
Okay, great. There we go.
Okay. So we've got our sequence of integers. That's much better.
That's
right?
better. There we go.
And we want to define its inversion set. I'm going to denote that by capital INV. Of pi. And it's just going to be the set of all pairs of indices, ij, such that I is smaller than j and pi I is bigger than pi j. Right, so these are, you can think of these as the sets, pairs, which are out of order in pi. And the inversion number is just the cardinality it's still not liking this. That'll be little inv pi, which is just the cardinality of the set. Quick example. Geez, this thing really doesn't want to. Okay, let's see whether this works. So where do I need to go to get the, you said it's in settings? Okay.
Yeah, go to settings and go to whiteboard and desk, and then there's a thing that says reset desk whiteboard.
Right, reset.
Is it maybe the
Desk
battery?
whiteboard. Okay.
What about the battery? Did somebody say?
Oh, I was just wondering, maybe it's the battery of the
Of
thing.
the
that
controller?
needs- Yeah.
Oh, what was the comment?
The comment was, do your controllers still have batteries?
Uh, it's not saying it's low.
Yeah, usually
I
it'll say it's low if it's
yeah,
low on battery. Yeah, so
yeah,
your controller's probably okay.
yeah. And I replaced the batteries earlier.
Okay, great.
So, okay, so let's see whether this is any better. Well, that seems to be better. Suppose we had pi being the permutation 2, 4, 2, 1, 4. And I'm going to put the indices up above just so that we know what they are. 1, 2, 3, 4, 5. So where are out of order pairs? Well, the 2 and the 1 are out of order. So that would give me in my inf set a pair consisting of the first and the fourth index. And then what else do we have? The 4 and the 2 and the 4 and the 1 are out of order. And the 4 and the 1. So that would give me index pairs 2, 3. Now it's almost worse. Can you read that? What?
Barely.
Yeah.
Is it just not picking up somehow?
No,
looks like
it's
it's
picking
picking-
up too much. It's following my cursor even when I don't want it
That's-
to be.
Oh, that's funny.
So inf of pi is there's 3 pairs here. I'll try and write really carefully.
Don't you also have the 2 and the 1 pair in the middle?
Yes. So that was the 2 and the 1 pair was maybe I got this wrong.
No, so you
Oh,
got
no,
three,
no,
three.
no,
I
no,
think
no,
end
no,
is
no, no.
4, right?
Yes, yes, the 2 and the 1 pair also gives us one
Yeah.
more, so that would be
That'd be
3
3
and
comma
4.
4. Yeah.
So this inf would be
There we go. Hi.
4. Okay. Everybody clear what inv is? Great. Okay, so let's go on and go back to our example and take the corresponding generating function. So now we're going to take big F of Q, say, to be the sum over all the bit strings in B42 of Q to the inversion number. And let me just tell you what that comes out to be. It comes out to be the polynomial 1 plus Q squared plus, 2Q squared plus Q cubed plus Q to the 4th when you calculate it out. So let's check whether that, remember where did we get into problems last time? We got into problems when we were taking rotation and omega equal to I. That was the one that didn't work. Well, let's check. If I take from my group element just a single rotation, and I take for my omega I, what do I get? Well, F at I, what is F at I now? F at I is 1 plus I, then 2Q squared gives me minus 2, then Q cubed is going to give me minus I, and Q to the 4th is going to give me plus 1. So what happens here? Notice the I and the minus I cancel, right? That's a minus. It's hard to read. I apologize for this. What else cancels? The minus 2 cancels with the 2 plus 1s. So you get a grand total of 0. And remember, that was the number of things that was fixed. There was nothing fixed by rotation. So this is looking promising. Okay. But then we can ask, well, wait a minute. Okay, this looks like we have cyclic sieving, but is it even homomessic? Right? We don't know that from the get-go. So let me show you why it's homomessic.
Quick question, Bruce.
Yes.
Do you mind if I like rewrite some of your things that don't show up? Like on the left, I just rewrote your pairs.
Sure, go for it.
Because this
Go
way,
for
if
it.
something's if one of your strokes comes out like a plus looks like a minus, I could just fix it in the background,
Do it.
and you don't
Do
have
it.
to
Do it.
say anything. Okay, sounds
Absolutely
good.
do it.
I think it'll make it a little more smooth of
Exactly.
a lecture. Okay.
Exactly. Do you want to correct anything here before? Yeah.
Yeah, I'll
And
just
then-
make the eyes look better and things like that, and we could you
Right.
could just go on as I'm doing it.
Okay, because
I
I'm
won't
about
do
to get
it.
a new
Yeah.
whiteboard. Does that
Oh, I
matter?
see. Let me just fix this one plus, and then it'll look real nice for
Okay, great.
Next time somebody's looking at the notes. There we go.
Excellent. Okay. So here is the theorem that we're going to prove. So this is a theorem of Propp and Roby from their original paper where they defined homomessy for the first time. This is 2015. And it says that inv, the statistic inv, on BNK under rotation is K times N minus K over 2 messic. Okay. How are we going to prove that? Well, first claim is that if I have a bit string, there's another way to calculate the inversion number, and it's by the following sum. So you take all pairs I less than j, and then you multiply b sub I times 1 minus b sub j. Add all those up. Well, why can you do this? Well, think about it. Let's prove that claim. Well, it suffices to show that this sum gives you a 1 or a 0 in exactly when you have inversions, right? Because that will do it. So it suffices to show that this summand bi times 1 minus bj is 1 if we have an inversion. An inversion of in a bit string will look like what? A 1 followed by a 0, right? So if bi bj looks like 1 0, and it gives you 0 otherwise, right? And since these are all bits, this is clear. This product is clearly 1 or 0. The question just is, when does it give you which one? Okay, so but think about it. Let's look again at this product. Let's see. When is that going to be equal to 1? Well, that's only equal to 1 if both of the factors is 1, right? We don't have any fractions or anything else. So that's if and only if bi is 1 and 1 minus bj is also 1. But what is that telling you? That's telling you bi is 1 and bj has got to be 0. which is what we wanted. Okay, so everybody agree if we compute this sum, we've computed the inversions. Questions? Good, excellent. So
Oh, there's a
was that
question
a
here, I
question,
think,
Spencer?
Spencer.
Or... No, okay, not a problem. So another trick we're going to use is, well, let's take a look at this sum a little more closely, right? Just distributing this over here. This is the sum over all I less than j of bi minus the sum over all I less than j of bi times bj, right? So I claim that this second sum is easy to do. I claim that it's just k choose 2. Why is that? Well, think about it. What are we summing here? We're summing products bi, bj. We're only going to get something non-zero if both of those are 1, right? And how many ones do we have? K. And we have to, how many of them do we have to choose? We have to choose 2 of those to get a 1, right? So this is since we only get bi, bj equal to 1 if they're both 1s. And there are k 1s. Let's call this 1 so we can, equation 1, so we can refer back to it. Now we're going to use the trick that we used before. What was the trick that we used before in the other one? Rather than looking at orbits, we looked at superorbits, right? Let's look at superorbits. So it suffices to show that inv of an O over the cardinality of O equals what it's supposed to be. For superorbits O. Right, we were using O star before, but let's just use O here to make life simple. And remember, in this case, all of our superorbits have size n. That will be useful in a second. Okay. So what is this inv then going to look like? Well, by definition, it's the sum over all bit strings in your superorbit of their inversion numbers. And now using this expression 1 that we had over here, that's going to be the sum over all b in my orbit of this first expression and what's going to happen to the second one? Well, the second one's constant. So we're just getting it n times. So that's going to be minus n times k choose 2. And let's call that 3. So now we just have to figure out this inner sum. Everybody agree? Okay. So my claim is, claim B, it is not hard to show using the superorbit that this sum is actually k times n choose 2. And I'm going to put that on as an exercise so you can have some part in proving this theorem as well. So put everything together by equations 2, 3, and claim B. Let me just move this a little bit. What is our average? Well, it's equal to 1 over n, and then we had kn choose 2 for the first term, and we had n k choose 2 for the second one. But now look, 1 over n cancels into n choose 2, right? And that gives me just n minus 1 choose 2. This 1 over n also cancels that n, and that gives me k times k minus 1 over 2, just the k choose 2. What's common to both? K. And if you factor out the k and take the difference, that gives me k times n minus k over 2, which is what we wanted. Amazing, but true. Okay, any questions? Okay, excellent. Very good. So now we want to show that we also have cyclic sieving, right? So let me give you some standard notation that we're going to use a lot. So if I've got a non-negative integer, then I'm going to let brackets n be the numbers from the integers from 1 to n, okay? And if x is a set, we're going to let x choose k. So notice this is like n choose k, except I have a set in the top. So this is going to be the set of all subsets of x that have k elements in them. So it is the set of sets counted by n choose k, if n is the cardinality of x. Okay. Well, so we're going to be talking about subsets here rather than bit strings, but there's a well-known bijection here. Right? It's the bijection that basically takes a bit string to its set. So if I've got a bit string bnk, let's call the bijection beta. So you take your bit string b1 through bn, and you're going to send it to some set y, where the ones tell you which elements to put in y. Right, so quick example. What would the string go to? what set?
2, 3, 5.
Yeah, I think I hear somebody saying it. 2, 3, 5, right? Because we've got ones in positions 2, 3, and 5, and we would be considering this as a subset of bracket 6, right? Because we've got 6 bits. Okay, hopefully this all this is pretty standard stuff. Questions? Okay. So continuing on our way, we're going to let German fractor Sn. Let's see if I can write that a little bit better.
Nice.
Be my favorite group, the symmetric group. Of permutations of the numbers 1 through n. Okay. And I'm going to consider the following cyclic subgroup. Call it Cn, and it's the group that's generated by the n cycle n minus 1 down to 1. Now, you might think it would be more natural to look at the cycle that sends, right? This is the backward cycle rather than the one that sends 1 to 2, 2 to 3, et cetera. It's the one that goes down. You might think that the other cycle would be more natural. It turns out to make what I'm about to do have the same conventions as what we're doing is for rotation. I need to use this cycle. That's why I'm doing this in this case. So well, then G is going to act on, so, right? So G in Cn acts on elements of brackets n choose k, right? So the k element subsets of 1 through n in the kind of obvious way. If I want to act with G on a set, I just apply G to each of the individual set elements. Thanks for cleaning this up,
Oh, no problem.
Maria.
I want to be as inconspicuous as possible.
Yeah, no, it's really good you're doing this. Thank you.
Yeah, it's no problem.
Let's take a quick example. Our usual example. What is the cycle 4, 3, 2, 1 going to do to the set 1, 4? Well, 1 gets sent to what by that cycle? Yes, I see the right number of fingers up from Robbie, 4. And what does the 4 get sent to? 3, right? So it sends that to the set 4, 3.
Oh, I'm just as bad.
Oh, sorry.
There we
Go
go.
ahead. Go ahead and
No,
fix
no,
that.
that's okay.
Yeah.
No.
But compare this with what rotation does. What does rotation do? What is the bit string for 1, 4? It's the bit string 1, 0, 0, 1.
Mm.
When I rotate it, what are we going to get?
Oh.
0, 0, 1, 1. If I rotate the bit string for 1, 4, I get the same thing as if I apply this cycle to the corresponding set.
Mhm.
This means that these two actions are going to have the same orbit structure. This takes a little while to see. Right now, let's just believe it. This is something called equivariance, which we're going to spend a lot of time talking about in the last couple of lectures. For right now, I just want to point that out, that we haven't really changed the orbit structure. We've just changed the way we're looking at it, okay? Questions about that? Okay, well, just a few more definitions and then we can state the cyclic sieving phenomenon. So I have to tell you what the inv generating function looks like here. And these are, again, standard definitions. So the Q analog of a number n, non-negative integer n, it's denoted brackets n sub q, and it's the polynomial 1 plus q plus q squared, etc., up through n minus 1, first power, n minus first power. And the reason for that is that if I plug 1 into this polynomial, I'll be adding 1 to itself exactly n times, and I get n back. Then there's the Q analog. So that's the Q analog of n. Q analog of n factorial then rather than taking the product of the first n integers, we take the product of the first n polynomials. So that's going to be brackets 1 sub q, brackets 2 sub q, etc., up to brackets n sub q. And then finally, the Q analog of the binomial coefficient, sometimes called a Q binomial coefficient or Gaussian polynomial. You just take the normal expression that you would get in terms of factorials and you Qify everything. Okay, so those are the definitions. I should say that sometimes to make things easier to write, I'm going to drop the subscript Q's. Now, that could cause some confusion with the Q analog of n because we're also using brackets n for the numbers 1 through n. But hopefully context will make it clear. If it doesn't, just ask which of the two I mean, and I'll be happy to say something. Was there a question out there? I thought I saw maybe a hand. Okay, great. These are fairly standard definitions. So here's the cyclic sieving phenomena, which we can now state. So this goes back to a paper of Reiner, Stanton, and White, which is where they first identified this phenomenon. So this is a paper back in 2009. And it says that the CSP is exhibited by the triple consisting of the K element subsets. Actually, let's do this down here. Yeah. The K element subsets of 1 through n. This group generated by the reverse cycle. And the Q binomial coefficient n choose k. Okay. So remember, how does cyclic sieving work? We need to calculate fixed points And then we need to calculate what happens when we plug in roots of unity and show that we get the same thing, right? That's the way cyclic sieving works. So we'll have enough time today to show you the fixed point calculation. And then tomorrow we'll worry about the plugging in of the roots of unity. Okay. So
One quick question, Bruce. Should
yes,
there be
quick.
a sub Q on the bracket n choose k, or you just use
Remember,
bracket?
I have this convention that, yeah, that
You're just
I will
dropping
leave
it.
it out
Okay.
when convenient.
Sounds
And
good.
if you ever have a question about exactly what I'm talking about, then please ask. But
Sounds
yes,
good.
I mean, you put it in or leave it out. It doesn't matter. Those are considered the same thing.
Sounds good.
Other questions or clarifications?
Bruce, I do have another question. So
Yes.
I understand that the theorem that you're gonna prove kind of relates back to the CSP of the rotation B and K.
Yes.
That one?
And it's because of that. Remember when I was talking about how you get between bit strings and sets
Yeah, the
using this beta map?
equivariant map.
That's the connection.
Yeah, but the thing that got me concerned was like before that you prove the homomorphism property of the inversion number. Does
Right.
that like relate to CSP
Oh,
somehow?
that's a
Or
great question. Yes. So on the exercises, you will see that I give you the exercise to prove that the generating function for inversions gives you the Q binomial coefficient. So those yes, those have to match up, and they do. But
okay, so
and
if I
you'll be proving
have
that during the. I'm sorry. Say what?
yeah, if I have like generally if I have a group action and I also have like I want to construct a function such that it satisfies CSP. Like, do we have a general method?
No, that's the beauty of CSPs. You have it's kind of like magic. Coming up with the right generating function is often not easy. It is not intuitive.
Cool, thank you.
Sure. Other questions? Okay, so this is going to be doing by a sequence of claims. So the first claim is and this is just for general group actions. It doesn't have anything specific to do with this theorem. Let G act on X. And so on the K element subsets in the way that we showed, we will want to calculate fixed points. So if little g is an element of G and S is one of these K element subsets, then G fixes S. Actually, let's put this down here. G will fix S if and only if S is a union of cycles of G. Now, what do I mean by that? Well, remember, because cycles aren't sets, they're ordered sets. I mean, take cycles, throw away the order on them, and then just take their union. Let's do an example. I think an example will make this clear what I mean by this. Suppose I have G being this group element in S4, and I suppose I'm looking at it as acting on the two element subsets of 1 through 4. What are going to be the fixed points? Well, remember, I have to get two element subsets by taking cycles of G and putting them together. How could I do that? Well, one possibility would be just to take the first cycle, right? If I just take the first cycle, that is a 2-element, and consider it as a set, that is a 2-element subset of 1 through 4. Is there another way to do it? Nicholas, was that a hand or no? Is there any other way I can get a 2-element subset by taking cycles and putting them together? Yes, exactly. You could, right? The 2 and the 4 are fixed points. I could put them together, and that would give me a 2-element subset. So I just put these subsets together. Okay. See, is it clear what the statement of this means? Good, because this is also going to be something that's on your exercises.
Mhm.
Okay, so here's the second claim then. So this will give us the fixed points. If I have an element of my group Cn, and it has, say, order D, then I claim that the number of fixed points, actually, let me put this on the next slide. I think it'll be better there. So claim B. So if G in Cn has order D, then the number of fixed points of G acting on the K element subsets, one of two things. It's either N over K, choose D over K, sorry, N over D, choose K over D, and this is if D divides K, and it's 0 otherwise. Okay, so clear what this is saying. So we just, the number of fixed points is a binomial coefficient, as right, in order for this binomial coefficient to be well defined, D's got to divide K because the bottom is K over D, and otherwise it's 0. And the proof is really easy given the first claim. Okay, so remember, G is this cycle, or it's in the group generated by this cycle. So that means that G is a power of this cycle. And it has, of course, degree D. What do powers of a single cycle look like? They have a disjoint decomposition where all of the cycles in that disjoint composition have what? The same length,
Divide.
right? They're all of the same length. And if we want this thing to be of order D, what must the length of those cycles in the disjoint composition be?
D.
They have to be D cycles, right? Because that's the only way that then the Dth power of them will all be the identity. So this is saying, implies that G has a disjoint cycle decomposition C1 through Cn over D, where each cycle has length d, and there are going to be n over d cycles, right? Because we had n things total, and we need to put them into the d. Each cycle is of length d. Everybody, so this is for all I. Everybody agree with that? Okay, but remember, by what we just showed you, by the first claim, S is fixed under this action if and only if S is a disjoint union of some of the CIs. Right? That was what claim A said. But now think about it. First of all, let's take the case where K doesn't divide D. Is it possible to write S as a disjoint union of a bunch of D element sets if K doesn't divide D? No, right? They're all D cycles. When you put them together, you're going to get something which has got a multiple of D elements in it. Everybody agree that's not possible in that case. So the number of fixed points is going to be 0, right? Because that's the number of ways of doing it. So in that case, so if D does not K, divide K, this is impossible. So the number of fixed points is clearly 0. Well, what happens if D does divide K? Now it's possible to do it. Well, how many ways could we do it? Well, remember, we've got we're trying to put D cycles together. How many total elements do and we want to get K total elements. And how many D cycles do we have to choose from? N over D, right? And we need to pick enough cycles so that we get a total of K elements. So how many of those cycles do we need to pick? K over D of them, right? So, right, the number of S, number of fixed points, is the number of ways to pick K over D cycles C sub I from N over D total. But almost by definition, that's this binomial coefficient. And so we're done. Everybody, any questions about this argument? Great. So what we're going to do next tomorrow, right? This is only one side of the equation. And the other side of the equation, we're plugging in a root of unity. We need to show that when you plug in that root of unity, you get exactly this formula that we just wrote down.
Mhm.
Mhm.
And that's what we'll do. That's how we'll start off tomorrow.